I'm Facundo Agriel. I'm a software engineer at Dropbox, and today I'm going to be talking about Magic Pocket, which is an exabyte scale blob storage system. Okay, let's get right into it. So Magic Pocket is used to store all of Dropbox's customer data, and we also have many internal use cases. At its core, Magic Pocket is a very large key value store where the value can be arbitrarily sized blobs. Our system has over 4 nines of availability. We operate across 3 geographical regions in North America. Our writes are optimized for 4 megabyte blobs. Writes are immutable, and we also optimize for cold data. Our system overall manages over tens of millions of requests per second. A lot of the traffic behind the scenes comes from verifiers and background migrations. And currently deployed, we have more than 600,000 storage drives. And all of this also utilizes thousands and thousands of compute machines. Okay, let's talk about the most important component of Magic Pocket, which are the object storage devices, which we call OSDs. So this is an actual OSD in one of our data centers. You can see all the drives in here. And typically per storage machine, we have about 100 disks per OSD. We utilize SMR technology, and each storage device has over 2 petabytes of capacity. Let's talk about why we use SMR technology. So SMR stands for shingled magnetic recording, and it's different from the conventional perpendicular magnetic recording, or PMI drives, that allow for random writes across the whole disk. With SMR, the trade-offs are that you offer increased density by doing sequential writes instead of random writes. So as you can see here, you're squeezing tracks and SMR drives together, which causes the head to erase the next track when you walk over it. But in this case, you can still read from it. It just that you can't just randomly write in any place that you want. And this is actually perfect for our cases based on the workload patterns that I just told you about. So this actually ends up working really well for us. SMR drives also have a conventional zone outside the diameter that allows for caching of random writes if you need to. And this conventional zone, it's typically less than about 1% of the total capacity of the drive. Okay, let's talk about the architecture of Magic Pocket now. So at a very high level view of our system, we operate out of 3 zones. So we operate out of a West Coast, Central Zone, and an East Coast. And the first abstraction here is a pocket. So a pocket is a way to represent a logical version of everything that makes up our system. So we can have many different instances of Magic Pocket, and some versions of that could be a test pocket. So something in like a developer desktop, you can run an instance of Magic Pocket. We also have a stage pocket, which is before our production zone. And databases and compute are actually not shared between pockets. So they operate completely independently of each other. Okay, so now that we have a high-level view of what a pocket is, let's talk about the different components. So let's get into what a zone is. So within a zone, we have the first service here, which is the front-end service. And this is the service that we expose to our clients. So all of our clients interact with us through this front-end service. This is what they call to make any kind of requests. And the types of requests our clients typically make are a put request with a key and a blob, a get request given some key. They might make a delete call They might scan for what hashes are available in the system. They might want to update some metadata on a specific key as well. And when a GET request comes in, what we first have to consult is the hash index. So the hash index is a bunch of sharded MySQL databases, and everything is sharded by this hash. So a hash is basically the key for a blob, and we simply just take the SHA-256 of that blob. Internally, we call those blocks, which are parts of a file, pieces of a file, typically no more than 4 megabyte chunks. And in the index, what you'll find is that a hash is mapped to a cell, which we'll talk about in a minute, a bucket, and we also have a checksum as well for that specific hash. And a cell is another isolation unit. So this is where all of the storage devices actually live. And so the index table just points to the specific cell and a bucket, so another level and direction where to go to in the cell. And the cells can be quite large, so they can be over 100 petabytes in size of customer data. They do have some limitations of how much they can grow, but as the system as a whole, if we are low in capacity, we just simply open up a new cell, so let's say cell 10. And that's how our system is able to horizontally scale forever, with some limitations, of course. All right, let's talk about what else we have in a zone. So another component that we have in the zone is the cross-zone replicator. So the idea behind the cross-zone replicator is that within Magic Pocket, we do cross-zone replication. So that means we store your data in multiple regions. And this is done asynchronously in the background. Once a commit happens and you know where your data is, we automatically queue it up into the cross-zone replicator so it can be moved over to the other zone somewhere else. We also have a control plane. So the control plane is basically manages traffic coordination within a zone in order to, for example, if we have migrations in the background, it generates a plan in order to not impede with live traffic. And we also use it to manage, let's say, reinstallations of specific storage machines. So for example, we might want to do a kernel upgrade or an operating system upgrade. The control plane will take care of that for us. And it also manages cell state information. So the cells have certain attributes as well about maybe, let's say, type of hardware that's involved in there and so on. And that's what it's doing. Okay, so we talked about a hash is mapped to a cell and a bucket. So let's get into what a cell and a bucket is. Okay, so within the cell, we have a bucket, and now we already went into the cell. So the first thing we have to do if we want to fetch our blob back is that we have to consult this component called the bucket service. So the bucket service knows about a few things. So it knows about buckets and volumes. And anytime you want to, let's say, as we're doing a fetch here, we first find the bucket. That bucket is actually mapped to a volume. And the volume is mapped to a set of OSDs. And the volume can be open or closed. There's a generation associated with it. And also volumes are of different types. So volume could be in some replicated or erasure coded state. So when we ask for a bucket, that volume will tell us which specific OSD has our blob. So let's say We go to bucket 1, map to volume 10, and then within the volume we find this OSD here. So we will simply just need to ask this OSD about our specific blob, and it'll hand it back to us. And that basically completes the way that we retrieve a blob from Magic Bucket. If you want to do a write, it's a little bit different, but essentially the same. It's just that the buckets are pre-created for us. So simply the front-end service needs to figure out what buckets are open for it to write to. So it will write to buckets that are open and ready to be written. So in this case here, if it's an open volume ready to be written into, what we do is we may write to this set of OSDs. So within a volume, it will be mapped to these 4, and that's where your data will be stored for that specific volume. Okay, let's talk about a couple other things within the cell. So another component that's very important is this coordinator. So the coordinator is not in the path of a request for a put or get call. It's actually works in the background. And what it does is it's managing all of the buckets and volumes, as well as all of the storage machines themselves. So it's constantly health checking storage machines. It's asking them what information do they know, and reconciling information from the storage machines with the bucket service in the bucket database. And other things that it does is that it will do erasure coding, it will do repairs. So if, for example, if this storage machine goes out, you'll need to move data to another machine. So it's in charge of doing that. It'll optimize data by moving things around within the cell. Or if there's a machine that needs to go offline, it will also take care of that too by moving data around to some other machine. And the way that it moves data around, it doesn't actually copy data itself. It's actually all done by this component here called the volume manager. And the volume manager basically is in charge of moving data around, or when we need to move data, how to recreate the new volume, when to recreate the new volumes, and so on. And I talked a little bit about some of the background traffic that we have. A lot of verification steps also happen within the cell, as well as outside of the cell, and we'll talk about that as well. Okay, let's talk about a little bit more about buckets and volumes, and what those are in more detail. So we have the concept of these 3 components. We have buckets, volumes, and extents. And you can think about a bucket as a logical storage unit. So I mentioned if we wanted to do a write, we write into a bucket, which is associated with the volume. And then finally, this other concept called an extent. And the extent is the actual, it's just about 1 or 2 gigabytes of data found on a disk. And so if we want to do a write, we simply figure out what open buckets are. So assuming we found, this bucket 1, we have to get the set of OSDs associated with those. And then when we do the write, we simply make a write within the extents themselves. And the extent information and volume information and the buckets are all managed by the coordinator I talked about before. So if any data is missing or things like that, you can always get it from the other remaining storage machines. And the coordinator will be in charge of finding new placement for that extent that was deleted. So buckets, think about it as logical storage, typically 1 to 2 gigs. Volume composed of 1 or more buckets, depending on the type. A set of OSDs, type again, whether it's replicated or erasure coded, and whether it's open or not. And once we close a volume, it is never opened up again. Okay, let's talk about how we find the actual volume in the storage machine, or the actual blob in the storage machine. Okay, so we have the blob. We want to fetch the blob. We know now the volume. We know that the volume is associated. These OSDs are supposed to have our blob. So simply what we do is that we store the address of these different OSDs, and we talk directly to those OSDs. Let's move over here. So we talk directly to those OSDs, and the OSDs, when they load up, they actually load all the extent information and create an in-memory index of which hashes they have to the disk offset. So for example, if you had some hash of blob foo, it'll be located in disk offset 19292. And in this case, this volume is of type replicated, so it's actually not erasure coded. So we have the full copy available in all the four OSDs mentioned here. And this is for fetching the block. If you want to do the put, it'll be of the same type. It'll be 4x replicated. And you'll simply do a write to every single OSD itself. And we do the request in parallel. And we don't act back until the write has been completed on all of the storage machines. Okay, so let's talk about the difference between a replicated volume and an erasure coded volume and how we handle that. So obviously 4x replication, and we have two zones that we replicate the volume to. That can be quite expensive. So overall, this would be 8x replication, and that's very costly. So we want to be able to lower our replication factor to make our systems more efficient. So this is where erasure codes come in. So when a volume is in a replicated state, after a few hours, the volume will be, or shortly after the volume was almost full, it will be closed and it will be eligible to be erasure coded. So erasure codes are able to help us reduce the replication costs with similar durability as straight up replication. So in this case, we have on erasure code, let's say this is Reed Solomon 6 plus 3. So we have 6 OSDs and we have 3 parodies over here. And the idea is that we call this a volume group or grouping, and you'll have the blob, a single blob in one of the data extents. And then if you lose any one of these OSDs, you can reconstruct it from the remaining parodies and the other data extents. Okay, let's go into a little bit more detail here on erasure coding. Continue this conversation. So yeah, in this case, as I mentioned, you can read from other extents and parody for the reconstruction. And as you can imagine, this area becomes really interesting. There's going to be a lot of variations of erasure codes out there with many different trade-offs around overhead. So let's talk briefly about that. So for erasure codes, they can be quite simple. You can use something like XOR, where you can reconstruct from the XOR of other things. Or you can use very custom erasure codes. And there's a lot of trade-offs. For example, if you want to do less reads, you might have higher overhead. if you want to tolerate more failures, the overhead, so your replication factor is likely to increase if you want to tolerate multiple failures within that volume group. And this is a very interesting paper by Microsoft called Erasure Coding in Windows Azure Storage by Hung and others. And this came out a few years ago, but it's super interesting. And it's something very similar that we actually do within Magic Pocket as well. So I mentioned the example before around with the example with Reed-Solomon 6.3. So 6 data extends and 3 parities. So with the codes that they came up with called least reconstruction codes, they have a concept of optimizing for read costs. So in Reed-Solomon 6.3, the read costs, if you have any failures, is going to be the full set of all the extents here. So your read penalty will be, let's say, 6 here. Well, they came up with equivalent codes such that for one type of data failures, you can have the same read costs, but a lower storage overhead. So in this example here, their storage overhead, their replication factor is roughly 1.33x, where the same replication factor with Reed-Solomon is going to be 1.5. So it may not seem like a big savings, but at a very large scale, this ends up being quite a lot that you end up saving. Of course, this optimizes for one failure within the group, which is typically what you'll see in production. If you can repair quickly enough, you will hardly see more than one type of failure within a volume group. Those types of failures are a lot rarer, and they typically don't happen that often. So it's okay to make the trade-off here with that. And yeah, just to iterate, 1.33x overhead for the same as a Reed-Solomon code. So super interesting paper. You can even continue to lower your replication factor, and you can see here it far outpaces Reed-Solomon codes for similar overhead, lower overhead, but similar reconstruction read costs. Yeah, and typically for LRC 1222, you can tolerate any 3 failures within the group, but you can't actually tolerate any 4 failures. Only some of them can be actually reconstructed. It's just simply not possible. Okay, so can we do better than this? Notice that, we have a 2x overhead for cross-zone replication. So even though our internal zone replication factor is quite good and ideal, we still have this multi-region replication that we do. So what else can we do? So a while ago, the team made some really good observations about the type of data that we have in our systems. So the observation was that retrievals are for 90% of data uploaded in the last year. So even as you go here through the graph, you can see that 80% of the retrievals happen within the first 100 days. And this is quite interesting, which means that we have a bunch of data that's essentially cold and not accessed very much. So we want to actually optimize for this workload. So we have a workload with low reads. We want similar latency to what we have today for the rest of Magic Pocket. And the requests don't have to be in the hot part of requests, meaning we don't have to do live writes into the cold storage. It can happen at some point later. And data, and we want to keep the same similar durability and availability guarantees, but again, lower that replication factor from 2x further down. And another thing that we can do here is we can make use of more than one of our regions. Okay, so now I'm going to talk about our cold storage system and how that works at a very high level. So the inspiration came from Facebook's warm blob storage system. There was a paper that was written a few years ago and had a very interesting idea there. And the idea is as follows. So let's say you have a blob and you split it in half. So the first half is blob 1 and the second half is blob 2. Then you take the third part, which is going to be the XOR of blob 1 and blob 2. And we call those fragments. Those fragments will be individually stored in different zones. So you have blob 1, blob 2, and blob 1 XOR blob 2. So now, if you need to get the full blob, you simply need any one combination of blob 1 and blob 2, or blob 1 XOR blob 2, or blob 1 and the XOR over here. And you need to have any of the two regions to be available to do the fetch. And if you want to do it right, you have to have all regions fully available. And again, this is fine because the migrations are happening in the background, so we're not doing them live. So let's talk about some of the wins that we get from our cold storage. So we went from 2x replication to 1.5 replication, and this is a huge amount of savings. So this is nearly 25% savings from a 2x replication that we had. Another win around durability is that the fragments themselves, they're still internally erasure coded. And the migration, as I said, is done in the background. And when you do the fetch from multiple zones, that actually endures a lot of overhead on the backbone bandwidth. So what we do is we hetch requests such that we send the request to the two closest zone from where the originating service is at. And then if we don't hear response from any one of the from the two zones over some period of few hundred milliseconds, we actually fetch from the remaining zone, and that is able to save quite a lot of on the backbone itself. Okay, let's move over to some operational discussions on Magic Pocket. So the first component that I want to talk about here is how we do releases. So our release cycle is around 4 weeks end to end across all our zones. We first start off with a series of unit or integration tests before the changes can be committed. And unit and integration tests typically run a full version of Magic Pocket with all our dependencies. And you can run this in a developer box fully. We also have a durability stage. So the durability tester itself runs a longer suite of tests with full verification of all the data. So we'll do a bunch of writes, and we'll make sure that the data is all fully covered. And it's about 1 week per stage here. And this is to allow the verifications to happen in each individual zone. So typically we can do all the verifications for metadata checks within 1 week. And the release cycle is basically automated end to end. We have checks that we do as we push code changes forward, and they'll automatically get aborted, or they will not proceed if there's any, let's say, alerts and things like that. And just for some exceptional cases, do we have to take control. All right, let's get into verifications. So we have a lot of verifications that happen within our system. So the first one is called the cross-zone verifier. So the idea behind this is that we have clients upstream from us that know about data, so files, and how that maps to specific hashes in our system. So the Crosstown verifier is essentially making sure that these two systems are in sync all the time. And then we have an index verifier, and the index verifier is scanning through our index table, and it's going to ask every single storage machine if they know about that specific blob. We won't actually fetch the blob from disk. We'll just simply ask, hey, do you have it, based on what it recently loaded from its extents that it's storing. Then we have the watcher, and the watcher is a full validation of the actual blobs themselves. And we validate we do sampling here. We don't actually do this for all of our data. And we validate this after 1 minute, an hour, a day, and a week. And then we have a component called the trash inspector. And this is making sure that once an extent is deleted, that all the hashes in the extents have actually been deleted. So it's a last minute verification that we do. And then we also scrub or scan through the extent information, checking a checksum that's on the extent themselves. Okay, let's go to more operations. So we deal with lots and lots of migrations. So we operate out of multiple data centers. So there's migrations to move out of different data centers all the time. We have a very large fleet of storage machines that we manage. We have to know what is happening all the time. And there's lots and lots of automated chaos going on. So we have tons of disaster recovery events that are happening to test the reliability of our system. And operating Magic Pocket at this scale is just as difficult as the system itself. So just not counting Magic Pocket. So, okay, so some of the operations that we do is around managing background traffic. So background traffic accounts for most of our traffic and disk IOPS. So let's say the disk scrubber is constantly scanning through all disks and checking that checksum on the extents. We do a couple of things. So traffic by service can be categorized into different traffic tiers. Live traffic is prioritized by the network. So we're okay with dropping, let's say, background traffic. And I talked about the control plane, but it generates plans for a lot of the background traffic based on any forecasts that we have about, let's say, a data center migration that we need to do, the type of migration that we're doing, maybe it's for cold storage, and so on. Around failures, couple interesting notes. We repair about, let's say, 4 extents are repaired every second. The extents can be anywhere from 1 to 2 gigs in size. We have a pretty strict SLA on repairs, less than 48 hours. It's fine if we go over this, but typically, because the 48 hours is baked into our durability model, we want to keep this as low as possible. And OSDs get allocated into our system automatically based on the size of the cell, the current utilization, if there's any free pool within the data center they're operating in. And we have lots of stories around fighting unknown single points of failures, like SSDs of certain variety failing all around the same time. We have to manage all those things. Another note on migrations, we have lots of them. 2 years ago, we migrated out of the SJC region. There was a ton of planning that went behind the scenes for something like this to happen. I'll show you a quick graph of a plan for our migration out of SJC. So this is the amount of essentially data that we had to migrate out of SJC over the period of time. The light red line is the trend line, and the blue line is about the what we were expecting. So initially, when we started the migration, it was going really badly over here. And then over time, we got really good. And then we had this like really long tail end that we didn't really know how to address. So for these migrations that are very large, hundreds of petabytes in size, there's a lot of planning that goes on behind the scenes. We have to give ourselves extra time to make sure that we can finish it in time. Okay, and forecasting is another very important of managing a storage system of this scale. So storage is growing constantly. Sometimes we have unexpected growth we need to account for and absorb into our system. We may have capacity crunch issues due to supply chain going bad, let's say like COVID disruptions. So we always need to have a backup plan as soon as we kind of figure out that there's problems up ahead, because it takes so long to actually get new capacity ordered and delivered to a data center. It's not instantaneous. And finally, we do try and our forecasts are actually directly fed into the control plane to perform these migrations based on what our capacity teams tell us. Okay, so in conclusion, a couple of notes that have helped us manage Magic Pocket are protect and verify your system. So always be verifying your system. This has a very large overhead, but it's worth having this end-to-end verification. It's incredibly empowering for engineers to know that the system is always verifying itself for any inconsistencies. And at this scale, it's actually very much and preferred to move slow. Durability is one of the most important things that we care about within our system. So moving slow is totally okay. Waiting for those verifications to happen before you deploy anything. Always thinking about risk and what can happen is very important to mindset that we have to keep in mind. Keeping things simple, very important. As we have, let's say, very large scale migrations, if you have too many optimizations, there's too much that you have to keep in mind for a mental model. That makes things difficult when you have to plan ahead or debug issues. And we always try and prepare for the worst. We always have a backup plan, especially for migrations or if there's any single points of failures within our system or when we're deploying changes. Make sure that things are not a one-way door. Okay, thank you. That concludes my talk. Okay, so the first question that I see here is, does Dropbox maintain its own data center, or do you partner with hyperscalers like AWS for co-location? So the answer to that is that we do a little bit of both, actually. So in North America regions, we actually lease our data centers. And in other regions where it doesn't make sense, we actually utilize, for example, S3 and AWS for compute as well. So a bit of a mix there.
Oh, so you leverage S3?
Yeah. So for example, in some European regions, and some customers there want their data actually to exist locally in their region for various compliance reasons. So in those cases, we actually utilize S3 because we don't have data center presence there.
Okay.
Yep.
And then do you use any type of compression of the actual data before storing?
We don't compress the data before storing it. So once the data is actually uploaded in our servers, that's when we do compression and encryption. So the data is encrypted and compressed at rest. And there's obviously trade-offs with that. So if you were to compress data on the clients, we have many different types of clients, from desktops to mobile, etc. So it can actually be quite expensive for the user to do that. So.
Okay, there's another question here. Just curious, for SMR disks, how does it cost compared to others? To other options, I guess.
Yeah, so we work very closely with different hardware vendors to basically adopt always latest hard drive technology. And a few years ago, probably maybe 5, 6 years ago now, we started utilizing SMR technology very heavily. So I talked about the trade-offs in the talk. Um, and yeah, compared to PMR, so traditional drives, SMR is a lot cheaper given the density. So I can't talk about exactly the costs on a per gigabyte basis, but it is significantly cheaper, and hence why we're able to. It works so well for us, and we save a ton of money by adopting SMR technology. And then, yeah, so we actually published some information about the read speed and IOPS performance on SMR versus PMR. So in the end for us, because we have sequential reads and writes, it didn't make too much of a difference. So there's some latency differences with SMR, but given our workloads, it's actually pretty comparable to PMR. Because again, we don't do kind of these random writes and so on. So works very well for us. Any other disk type other than SMR you may also consider in the future? Again, so the industry is moving to various technologies in the future. So SMR is sort of hitting capacity limits over the next few years. So to give you some idea, the latest drives today with SMR are coming out this year at about 26 terabytes per drive, which is huge. But different vendors obviously looking out 3, 4, 5 years from now, it looks like laser assisted technology is going to be the next big thing. So look up for HAMR, for example, technology and so on. And those drives are expected to increase density to 40 terabytes within the next few years. So that looks like that's the next big thing that's coming for new drive technology.
I don't know if you covered this, but do you have like tiered storage, just less recently accessed storage? Do you do that behind the scenes?
Yeah, so we don't do tier storage. So what we used to have is we used to utilize SSD drives as a cache for writing on a per OSD device basis. So the problem that ends up happening is that became our limiting bottleneck for writes. And so we actually ended up getting rid of that recently. And we're able to get a lot more write throughput across the fleet in order to save on that. So the other thing that I talked about is colder writes, which we utilize our cold storage tier, but it's still on SMR drive, backed by SMR. And then we have explored, for example, using SSDs more heavily and so on. So that's actually something that we might leverage. It's just actually incredibly hard to do caching well at this scale for various reasons, protections and verifications, inconsistencies. All that stuff is really hard once you go through the motion. So that's one of the limiting factors. But for a cold storage tier, because we built it on top of existing infrastructure, it was quite straightforward to build on top of that. So
are there any, I mean, you've seen this system, I guess, in evolve and for a few years now. What do you have on the horizon that you'd like to see like built, or you'd like to build or design into the system?
Yeah, I think for us, there's always a few different things. So the steady state kind of status quo that we're kind of looking into is continue to scale the system for continuous growth, right? So we're growing at double digits per year, right? So that typically means that in 3, 4 years, we essentially have to double the overall capacity of our system, right? And so when that happens, that has a lot of implications for our system. So a lot of things that you thought would be able to continually scale you actually run into various types of limited vertical scaling limits. And so that's something that we're actively looking into for next year. And then the other ones are around having more flexibility around our metadata. So we use MySQL behind the scenes, sharded MySQL, but that has its own set of problems around being able to manage MySQL at that scale. If you want to easily add new columns and so on, that's also a huge pain. If you want to continue to kind of scale that up, you also have to completely do a split, and that's costly. So most likely our metadata stack will change next year, and that's kind of what we're looking at. And then again, the last one is hardware advancements and supporting, for example, Hammer once it comes out, and being able to get ahead of the curve on that is something that we're always continually supporting as well.
Do you have any war stories that come to your mind that, parts of the system that kind of woke you up late at night, burned you, and you guys had to jump on it and come up with maybe a short-term solution, long-term solution? Are there like any interesting war stories that you'd like to share that you feel you can actually?
Yeah, there's a lot of interesting stories that we've had to deal with over the years around memory corruption and so on, and finding areas within our system that haven't had proper protection. So we do have, for example, corruptions are happening all the time, but because of these protections, verifications that are going on behind the scenes, we don't really notice them, and the system fails gracefully. But once in a while, we'll get woken up in the middle of the night for some new random corruption that we didn't know about. And one of them actually happened recently. Data is fine because it is replicated many regions, and even if the data is corrupted, the data still continues to live in what we call trash, which is another protection mechanism where the data is deleted, but it's kind of soft deleted. You can still recover it. Anyways, yeah, we had kind of like a all hands on deck situation a few weeks ago where kind of this happened, and took many kind of late nights to kind of figure out where exactly things might be. Obviously, we don't log everything, so being able to figure out where the problem came from is very difficult. But I think we kind of tracked it down to one or two places now.
So like trash was filling up faster than you could sort of get rid of it, because the soft deletes were not real deletes, so you're running out of storage.
We always keep data around in trash for 7 days. That's part of the problem. It's the memory corruption. So we found just a single hash, single piece of data that ended up, we found that it was corrupted. And yeah, I was just kind of mentioning, like, being able to track that stuff down is very difficult. Even though you may have many different places where we do various checks and so on along the way. But yep.
Well, I see that we're out of time, but I want to thank you again, Facundo, for sharing your experience with us. And if people have questions for you, how can they best reach you?
Yeah, I'll be on Slack today. If you have any other questions you think about, I'm also on LinkedIn. Happy to chat with you there, accept your requests for any connections. Looks like there's one more question. I'll copy that and answer in Slack. But yeah.
Sure. All right. Thank you very much, Facundo.
All right. Thank you, guys. Bye.